place is hot. Can you do something about that?
Okay, I hear you. This place stay hot, rough. To make it be cool like ice water, I fit turn on the fan. You get fan for any particular area where you want make I focus on.
So hello guys and welcome back to the channel. Today we are learning about NE555 and PWM. So PWM, what's PWM? PWM is also known as Pulse Width Modulation, and then it's only for DC signals or DC, yeah. So for me to explain what PWM is, we have to understand how a DC signal looks like. So a DC signal typically looks something like this. So squares. So this is how a DC signal looks like. So for example, if our input is 12 volts, our low 0, our high is going to be 12 volts. So that's how it's going to be. So for that, 12 volts are high, 0 volts, 12 volts, 0 to 12, then 0 back, then 12, and then so on and so forth. That's how the whole thing is going to look like. So it's either it's at 0 or it's at 12. You get it? This is what a DC wave looks like. This is what a DC signal looks like. So it's either actively low or actively high, high or low. That's what DC is all about. Now in contrast, this is what an AC signal is going to look like. So this is just a bonus. So an AC signal looks something like this. So we have our positive and then our negative. So 0 here, and then it crosses the 0 mark to the positive side over here, comes down, passes 0, and goes back to negative. So it's alternating between positive and negative. That's how come we have the name alternating current, also known as AC. So that's the bonus tip for you guys today. So for AC, we can't have a PWM signal. Now this is our digital signal, our DC signal. So it's moving between 0, which is low, and 12 volts, which is high. For a PWM signal, it's going to do the same thing, but it's going to do it very rapidly. And that's where a word that we are going to be using today comes in, and it's called switching. And then yeah, you might be asking, what is switching? The switching is the same switching you know of. So for example, flicking your light switch on and off, that's switching. But in this case, you are doing it very rapidly. So you are switching at around like kilohertz of speed. So kilohertz, so very fast. So for kilohertz, like 20 kilohertz and above 24 kilohertz, you are like ultrasonic speeds. So at these speeds, very high, a human being can do this by himself or by his or herself. So by varying the switching speed, we perceive brightness. So at the highest switching speeds, that's at a duty cycle of 100, we perceive the speed as very high. So at that speed, it's like 0 to 12 is actually like at its normal high voltage. So if it's a 12 volt signal that we are inputting, is at 12 volts. 50% is varying between the 0 and 12, so it's a half of that. So half of 12 volts is going to be 6 volts. So it's switching to 6 volts very rapidly. You get it? So 0 to 6, 0 to 6, 0 to 6 very rapidly. So our eyes sees that as half brightness. So goes for 40%, 30%, 10%, and finally 0% duty cycle. So based on the duty cycle, we perceive a higher or lower brightness. So with that said, and with that out of the way, let's move on to the main concept of this video, that's using the NE555 as a MOSFET driver. So for us to understand this whole concept, we have to understand what a MOSFET is. So we now understand what PWM is. Now, take our microcontroller for example. So this sketch is just our microcontroller with its pins, could use this one. Let's try the Wi-Fi signal over here. So this is our microcontroller. Our microcontroller, which in this case is an ESP32, only outputs, so its output is 3.3 volts. Now, if you wanted to switch a load that was 12 volts, so in that case, we are going to draw a bulb. Pardon me if my bulb doesn't look quite nice. And yep. And then this bulb is rated 12 volts. 3.3 volts logic can never drive this 12 volts. Now the ESP32 is able to switch on small loads like those 1 volt to 2 volts to 3 volts LEDs, those very tiny ones. It can switch it on normally and not have any problem. But then for a 12 volts bulb like this, the ESP32 is not capable of doing that. So we need an agent to be able to switch that, and that's where something called a MOSFET comes in. So this is our MOSFET, and then 1, 2, 3. Now this is our MOSFET. Has 1, 2, 3 pins. Pin 1 is our gate. It takes the control voltage or the control signal. Pin 2 is going to be our source, and then pin 3 is our drain. Okay, now this MOSFET should be able to switch on this load. So at the source, we connect one end of the source to the load, and then one end of the load to our 12 volts, and then here our 12 volts bulb could be switched. Now at the control voltage, we could use the 3.3 volts from the ESP32 at the gate, but then there is something called gate threshold voltage. So a gate threshold voltage is the voltage at which a MOSFET turns on. The gate threshold voltage is just the voltage at which the MOSFET will start turning on. So it's like these DC motors, some of them are rated 12 volts, but then if you input 3 volts into it, it will spin, but it won't spin at its highest speed, right? But in MOSFETs it's different. It's the same phenomena, but in this case, if we are to supply the lower gate threshold voltage, the excess power is going to be emitted as heat. So our MOSFETs can heat up quite a bit. It will heat up. So in that case, the gate normally turns on at a certain voltage fully. In this case, for most MOSFETs that are not logic level MOSFETs, because there are logic level MOSFETs that can run at 3.3 volts and not have any problems. There are a lot of them out there that will run at 3.3 volts. Those are logic level MOSFETs, but those ones are more expensive, and then they are not even as efficient as normal MOSFETs. Now the ESP32, as I said, could actually drive this whole circuit, but then it will struggle to do so, and then there will be a lot of heat, no efficiency. But MOSFETs were made so that we can switch more efficiently, right? So in that case, we need an amplifier to amplify the 3.3 volts from the ESP32 to the gate to be able to drive it as its full voltage. Now we could use a BJT, an NPN BJT, which serves as that purpose, logic shifting. But in this case, we are not going to use that. We are going to use the NE555, as I said, because they can generate PWM outputs of up to 500 kilohertz. And then for ultrasonic switching, as I said, 24 to 30 kilohertz, sometimes 40 kilohertz or 50 kilohertz is more than enough to switch on this 12 volt bulb. So we are going to add the NE555 to our setup right now. So This is our NE555, has 8 pins. So 1, 2, 3, 4, 5, 6, 7, and then 8. Now these are the pins on the NE555. Pin 1 and pin 2 will be connected together, and then they will be connected to our ground. Pin 3 goes through a resistor to our MOSFET gates over here. So a 10 ohm resistor is more than sufficient. And the last pin over here, that's the pin 4, goes to our ESP32's output, so the PWM signal from our ESP32 to the pin 4, which is the reset pin. Pin 3 is the output pin. Now pins 5 and 7 are going to be connected together. Those are going to be connected to 12 volts or VCC, or 10 volts, whatever voltage switches on the MOSFET as its full voltage. So that's about 10 volts for most MOSFETs. And then pin 8 and 6 are left floating, meaning they are unconnected to anything. Now pin 3 is going to be connected to ground. So that's our drain. Let's wipe this, and then we are going to connect our drain to ground. Now this circuit is complete, but then what you have to do too is our ESP32 has to be connected to ground too, so a common ground for all of them. And then there you have it, we have our full circuit. So the NE555 here serves as the logic shift, and then it's outputting 12 volts to the MOSFET gate, and then it's switching the 12 volt LED or 12 volt bulb in this case. And then there we have it, from 3.3 volts to 12 volts. So the PWM signal that is going to be at the gate is going to be 12 volts. Then we have full brightness there. So I'm actually going to do a demo of actually how this whole thing works. Okay, so this is my circuit using the NE555 as a MOSFET gate driver. As you can see, that's the NE555 right over here. So let me explain how the whole thing works. So as usual, this is my microcontroller. This is an ESP32S3. These things are dead cheap right now on AliExpress, so you can get one for yourself. Very powerful and good. This is a potentiometer, so I just added this potentiometer there for manual control, but I haven't really set it up yet. Next, as you can see, I'm going to take you through the whole circuit. This is a MOSFET, so this is an IRFZ44N MOSFET. And then yeah, so let's take you through the connections and everything. So over here, our ESP32 is connected to 5 volts. That's the 5 volt rail, and then to ground over here. I don't know if the camera can get that. To ground over here. Let me zoom in there. So those are the two connections for the ESP32. Next is the second rail. So I use the second rail for 12 volts. So this is the 12 volts that is feeding into the NE555. So these are pins 5 and then pins 7. So pin 5 and 7 are connected to 12 volts. Pin 1 and 2, according to the schematic I did before, is connected to ground. The drain of our MOSFET is connected to ground too. Source is connected to one end of our load, and then the second end of our load. The gate is connected through this 10 ohm resistor to pin 3. That's the output pin. So the connection is done using this 10 ohm resistor over here. Now our signal is coming from the ESP32. So this gray, or the ash, this gray wire moves from pin 5 and goes straight to the reset pin on our NE555. So that's the control signal. And then in my code, I set it to a PWM frequency of 28 kilohertz. That's above ultrasonic speed. One thing to note is that they all have to share a common ground, and then one thing about ground is it's always 0 volts. So no matter what the VCC might be, whether 12 volts, 5 volts, 3 volts, or even 300 volts, ground is still 0, so they can all share a common ground. So I'm going to connect my load, which I made over here, this fan. Yeah, initially I was going to attach this to it. I made this fan that I was going to attach to it, but then because it's actually very heavy and this is just a very small fan rated 12 volts, there was a problem. It couldn't really spin at high speeds. But looking over here, I also have my flyback diode connected to the two ends of the load. I'm going to explain some things over there in a jiffy. So what I have done here right now is that, as you can see, my ESP32 is powered on. My power pack, that's the power bank I use for the ESP32, is currently off, and then this one I have here, I don't have a long enough cable to feed into the Type-C port, and then I wanted to do everything without having to connect to the Type-C port over here, so it's powered by the breadboard, and I'm getting power in from this phone over here. So the phone is feeding in 5 volts to my ESP32. That shows how efficient the ESP32 actually is, because it's not taking up a lot of current and it runs on 5 volts, very low. Now the next thing I wanted to show is, with the help of these banana clips over here, I have 12 volts or so on the second rail, and then what I'm going to do right now is I'm going to wire this to my load, which is this fan. So I'm going to wire it to my load right now. Okay, so wiring, so red to red, positive to positive. As I earlier explained, I have a diode there that serves as flyback protection. So inductive loads like this have coils, so the coils, when they stop, they send a very huge inrush voltage. It's called a inrush voltage, called a voltage spike, and then if not careful, that voltage spike can flow back into the whole circuit and damage some devices over here. That's why it's always advisable to use a diode across the terminals of your load. It serves as a flow back into the fan that we are controlling. So I'm going to connect my negative terminal to yep, and there we go. Now let's go into our Home Assistant, then trigger the fan. So as you can see, the fan is turned on right now. We are at low speed, medium, and then we can set it to high. So at high speeds, you can see that already. Can set it to off, low, then yeah. Now I'm going to demonstrate something. Let's look at something here. I turned on the load, that's the fan. See what happens. It doesn't move, right? Low, nothing happens. See, so low, nothing happens. This is because DC fans like this have a certain current that they have to start up at, and without those currents they won't really start up. So the torque that is needed to get these fans up and running isn't really there. So what I did is that I got these electrolytic capacitors. This is rated 68 UF. I don't know if I could get focus on that. Okay, so there we have it. This is rated 68 UF, as you can see, and then 400 volts. So this is an electrolytic capacitor. I got this from old laptop chargers, so you can get it from old laptop chargers, mostly the ones that are blown. So I got this from one that actually blew, so I just got this out of it. I salvaged parts from it, and I got two of them, so I modded them with my jumper cables to give them a little bit of exposed wires that I can work with. So I have two of that. So what I'm going to do is I'm going to connect this in parallel to my load, and you see what happens then. Okay, so now I have my capacitors connected in parallel to my load, and then let's go back to our console over here. Let's turn that on, and can you see that? Can you see that? There's a low. Can you see that? That is blowing like that's the lowest. To reference that, look at this paper I'm putting in front there. See how it's blowing? That's at its lowest speed, and see how much speed we can get at the lowest, set to medium and high. So this is very, very, very crazy. Now I'm going to explain how this works. So basically what is happening is that a capacitor stores electric current and voltage, so it charges up very rapidly. Unlike batteries, it's just like a battery, but unlike batteries, it stores up this energy very rapidly and uses it up very rapidly. So if you charge up a capacitor and then you connect a load to it, the load might only run for a split second, but at least it will run. So what is happening is that the voltage is charging up this capacitor, and when the capacitor is charged up, it's also sending the current it has stored back into the load, and with that the load has enough current to run at its full speed. So there are no compromises here. Now one thing to note is that you shouldn't get greedy and connect two of this in parallel. One is normally enough, because I made a mistake and then I was using an IRF Z520N, I think that's the name, or is it 540N, and those MOSFETs are rated only 10 amps. So using that one, the inrush current was too high using the two capacitors, and it ended up destroying that MOSFET. But this is a more higher rated MOSFET, the IRF Z44N. This one is rated 49 amps, so it's more than sufficient for this kind of switching. The IRF 520N2 is also good. It's actually a very good MOSFET, but it's only rated 10 amps, so it's mostly good for switching LEDs and all those things that don't really use up to high currents and all. So that's the whole setup here, and then as you can see, the fan is running. I can set all the speeds I want, and then yeah. Now one thing I wanted to also show off is using Google Assistant. Before that, let me show you what I have set up here. So I recently developed my own AI assistant using Home Assistant. So basically I have Gemini API, and then I've programmed this so that it's like human-like, so it can chat with you in pidgin and all those languages. So let's just give that a test. It's not really that perfect, but we are going to test it. So hello, how are you doing today?
Oh, chill, I did it today. I'm doing well, like jollof with them cook well.
Sorry
How
about
about
that.
you, my friend?
Let me turn up the volume.
You day Philly.
Let me ask that again. How are you doing today?
AI, today they be like Banku where you mix pepper plus fish. I dey enjoy rough. How about you, my poddy?
As
You
you,
dey catch cruise?
as you can see, it's trying to speak the pidgin, but then fast, it's not really up there, but at least it's able to speak the pidgin at least. So let's try something. Let's use it to control our. Turn on the DC fan.
Turn on the fan.
So as you can see, it turned that on, then it's running. Yeah, it runs normally. Turn off DC fan, and then it turned it off. Now
Turn off the fan.
you guys should look at something. Omo, this place hot too. If you do something about it didn't quite
I'm
get
sorry.
that. This place is hot. Can you do something about that?
Okay, I hear you. This place dey hot, rough. To make it be cool like ice water, I fit turn on the fan. You get fan for any particular area where you want make I focus on?
Yes, just turn on the fan in the living room. Turn on the fan. So as we can see, the AI actually understands context.
I don't turn on the DC fan.
Yeah, it understands
context. They blow well now.
It understands context and is able to understand what I'm saying, and then yeah, it speaks more like a human being. It can speak normal English too, a little bit of Chi, which isn't really perfect, and then yeah, local languages. So I'm going to work on that in the future, but that's to show you what AI can do in these kind of scenarios and applications. So almost forgot, if you need a video on how to set up a nice and beautiful dashboard like this, I'm going to do a future video. This is Home Assistant, and then I haven't done a video tutorial on it, but there are links to how to install it in my previous video, so you can check out my previous YouTube video based on ESPHome and Home Assistant. Yeah, so I was teaching how to get ESPHome set up. So on this microcontroller, the whole code isn't written in Arduino, it's written using ESPHome and YAML. So it's with YAML I'm able to integrate everything into Home Assistant, as you can see. So there is a whole tutorial on how to do that on my previous YouTube video, so you can check it out, and then like and subscribe. Cheers, and then I'll see you in the next video.